In this question, we're going to look at radicals. And the first part of the question asks you to explain why the reaction in equation 34.3 is classed as a propagation step. For this question, it's very useful to remind yourself what actually is the initiation, propagation and termination steps. Initiation step is where radicals are created from neutral species. So usually you will not see a radical in the reactant side of the equation, but you will see a radical in the product side. A propagation step is where a radical is used and produced. You usually see a radical in the reactant side of the equation as well as in the product side. A termination step is where radicals are used up to produce a neutral species. So you will see radicals in the reactant side of the equation, but not in the product. This question has told you that there are hydroxy radicals, so OH radicals, and nitrogen monoxide radicals within the equations shown. So we have to look at equation 34.3 and figure out what of these species are radicals. As you can see, there's a nitrogen monoxide radical in the reactant side of the equation, and there's a hydroxy radical in the product side. Therefore, this reaction is a propagation step, and this is because the nitrogen monoxide radical is being used up to produce a hydroxy radical. By stating this, this will give you 1 mark. The second part of the equation asks you to write the overall equation for the reaction sequence in the equations shown. For this, you have to look at the species in the reactant side of the equations and see what cancels out with the species in the product side. For example, in the reactant side of the equation, we've got an hydroxy radical. We've also got this in the product side, so these cancel out. In the reactant side of the equation, we've got an HOCO species. We also have this in the product side, so these cancel out as well. We have an HO2 species in the reactant side of the equations. We also have this in the product side, so these cancel out. There's a nitrogen monoxide radical in the left-hand side, and there is also a nitrogen monoxide radical in the right-hand side. Additionally, in the left-hand side, we've got a nitrogen dioxide as well as in the right-hand side, so these also cancel out, as well as the oxygen in the left and right-hand side. Overall, the things that haven't cancelled out is 1 molecule of carbon monoxide in the left-hand side of the equation. We've also got, in total, 2 molecules of oxygen in the left-hand side. So we can add these species to the reactant side of our overall equation. Now, let's look at the product side. We have 1 carbon dioxide molecule as well as 1 O3 molecule, which is ozone. So we can add this to the product side of the overall equation, which gives you an overall equation of carbon monoxide plus 2 molecules of oxygen going to ozone plus CO2. And this would give you 1 mark. Usually in equations, it's good to put down the state symbols next to the molecules. However, as it's clear that this is happening in the atmosphere, it's clear that all of these molecules are gases. Therefore, there isn't that much point putting the state symbols there.